Before I begin, I'd like to give a massive shout out and thank you to Jutmonk for telling about me on last night's shill show. So in this video, I want to continue the series of measuring the sun's shadow using a gnomon. I've already made a video, my last one, that talked about how I went about building my own, and here's a photo of that. And I also mentioned in that one that I was going to leave plans and instructions if you wanted to build your own in the description of that video. So go ahead and watch that video as well, and you'll see in the description the link. I'll also put the link to those resources in this video as well. In this one, I want to talk about the measurements that I took today. Last few weeks have been quite spotty at best in terms of taking measurements of the sun. I took advantage of the opportunity today. So after I took a bunch of measurements on the piece of paper, as you can see in this diagram, I then scanned the results in the computer. And you'll notice up here, I also, while I was taking the measurements of the end of the shadow cast by the gnomon, I also took lux readings of the sun at various points in time. This is going to be another set of videos on the lux readings, but that's not the exercise for today. The first two, the shadow extended well over the edge of the paper. I might make another video to talk about these two in particular and how you could go about finding those points. So at this point, I've got a series of measurements taken already on September 13th. We're a week away from the fall equinox, and this one here in particular, you'll note it was kind of really cloudy, and it was really hard to see the shadow, and then the sun just managed to peek out enough for me to capture it here. But at this point, the idea would be to use something like GIMP or any other photo editing software to locate the center point of the ball on the top of the gnomon. So this here would end up being where the ball was cast, and I would find the midpoint. So you're looking for the biggest, roundest part of the shadow, and then you just kind of line it up, and it would be right about here. So this one would probably be X 1595 right down here. It would be somewhere around 1595 and 1260 or thereabouts. So I would end up doing that for every single one of these data points and measure the point where the locating pin for the gnomon punched through the paper right here as well. So I would take all of these points and then put them in a spreadsheet like this. And I do plan on making this spreadsheet available as well to anybody who wants to use it. And this was something that I started working on back in April. And it is a very simplified version of the sun's movement. It does not take into account the fact that the Earth goes around the sun in an elliptical orbit. And so there's going to be some errors. And the idea was that you would end up calculating the time. So the idea was that for each one of these measurements, the computer would then calculate what it would think the ideal sun altitude and azimuth would be. Then it would calculate the gnomon's X, Y, and Z coordinates. But more than that, it would, and this is not going to be this video here, I'm just kind of going over some of these points, but you would end up putting in where you measured those values on from this piece of paper here. Then what it does is it displays on this graph, it simulates what the arc of that shadow length should be. So here's April 24th. And I did that for 3 days, April 24th, June 7th, and June 22nd. And you can see this one here is slightly off in some. And there's a few reasons behind that one. And again, this video is not to talk about these results. It's just to show you the process. So at this point, I'm going to pause, create another, copy the template to another spreadsheet tab, and then enter in these values, and I'll be right back. Okay, I'm back, and that was quite the rather interesting experience. So it turns out I've got some problem in some equation somewhere, and I was kind of scratching my head trying to figure out why something was going messed up. I'll have to investigate that, and that's going to be one of the other reasons why this spreadsheet won't be available anytime soon. So I got the equations right for certain times of the year, and you can see that the azimuth is working just fine and the altitude is working just fine. And then as soon as I got to closer to the fall equinox, the azimuth got all messed up. It's actually going towards the North Pole, and then it flips around and it kind of comes back towards the south. So this is all messed up. It's gonna be in one of these somewhere that I have to go and find out and fix the angles and the directions. So it's not entirely complete. It's going to take me a bit of time to kind of get this fixed up. Anyway, having said that, I put the values into the spreadsheet, and I was able to confirm that the blue line, actually let me just confirm this, then it's the 16th. So yeah, the blue shifted up. So the blue is the calculated position of the sun according to a very simplified model of the sun's movement, as I said earlier. The red is calculated from the measurements taken on the piece of paper. And I had to adjust, for some reason, I had to adjust the Neumann bias to get it lined up. And that might be because of these that are messed up as well. So I've got some cleanup to do. Anyway, there is still some work left to be done on the spreadsheets. I just wanted to point out that that was possible. That is what I was doing. And hopefully somebody else will find this interesting and want to grab that for themselves. If you like this video, please give it a thumbs up, like, subscribe if you're not already, and hit the bell to be notified of new videos coming out. Thanks for watching, and hopefully I'll see you in the next one very soon. Bye for now.